Good afternoon all. Myself Professor Sandeep Nemade, Associate Professor in Department of Electronics and Communication Engineering from Technocrats Institute of Technology, Bhopal. Here we are going to discuss the topic of VLSI design, CMOS processing technology. In this topic we cover the fabrication process, PWell process, NWell process, then basic twin tub fabrication process, CMOS latch-up, physical origin of CMOS latch-up, and latch-up triggering and latch-up prevention techniques. The CMOS can be fabricated using different processes such as NWell process for CMOS fabrication, PWell process for CMOS fabrication, and twin tub CMOS fabrication process. The fabrication of CMOS can be done in various ways. Here we are going to discuss the PWell as well as NWell fabrication process. It incorporates the several steps. We are going to discuss the steps one by one. This fabrication process can be done as follows. In step 1, primarily start the process with a P substrate. A substrate is taken with P doping that creates the P substrate. Over the P substrate, first we provide a oxidation layer, that is in steps 2 and steps 3. The oxidation process is done by using high purity oxygen and hydrogen, which are exposed in the oxidation furnace nearly approximately at 1000 degrees centigrade, and after the oxide layer is fabricated over the P substrate, a photoresist layer is fabricated. A light sensitive polymer that soften whenever exposed to light is called as photoresist layer, and it is formed over the oxide layer. Now in next step is the masking process. Here the photoresist is exposed to the ultraviolet rays through the NWell mask. Then in step 5, it is the photoresist removal process. Part of that photoresist layer is removed by treating the vapor with a basic or acidic solution. Part of that layer, which is mask, as shown in this figure, which is mask and ultraviolet rays is pass over it. Wherever the ultraviolet rays react on that photoresist layer, that portion become hard, and wherever the mask is appear, the ultraviolet rays will not react on that photoresist layer. So that particular layer is softened. Now next step is to remove the silicon dioxide using the acid etching process. This SiO2 oxidation layer is removed through the open area made by removal of photoresist using hydrofluoric acid. This is shown in the diagram. Now next process is removal of the excess photoresist layer. The entire photoresist layer is stripped off as shown in the figure below. Now in step 8 and step 9, step 8 is the formation of NWell process. This can be done by using ion implantation or diffusion process. NWell is formed, and in step 9 we remove excess silicon dioxide layer using the hydrofluoric acid. The remaining SiO2 layer is removed from this. Now in step 10, this is the deposition of polysilicon layer. Now by using the chemical vapor deposition process, CVD process, by using the CVD process, we deposit a very thin layer of gate oxide. Then in step 11, removing the layer barring a small area for the gates. Now except the two small region required for forming the gates gate region, over that NMOS and PMOS, the remaining layer is stripped off. In next step, that is step 12, it is the oxidation process, and here this an oxidation layer is formed on this layer with two small regions for the formation of the gate terminal of NMOS and PMOS. Now in step 13, this is the masking of the N diffusion layer. By using the masking process, small gaps are made for the purpose of N diffusion layer. The N type N positive ions are dopants are diffused or by ion implantation process or diffusion process. Now in step 14, that is oxide stripping process, the remaining oxidation layer is stripped off. And in step 15, that is the P diffusion process. Similar to the N diffusion process, the P diffusion regions are diffused to form the terminal of PMOS. Similarly, next is the next step is 16, 17 and 18, 19. In this case, in a thick field oxide is formed in all regions except the terminals of the PMOS and NMOS. Then metallization process is done, in which aluminum is sputtered on the whole vapor, and in step 18, removal of excess metal. This the excess metal is removed from the vapor layer. And in case of step 19, terminals are formed. The terminals of PMOS and NMOS are made from the respective gaps. And in step 20, assigning the names of the terminal of the NMOS and PMOS, that is source, gate and drain, and there is one more terminal called body terminal. So the among the fabrication process of the CMOS, NWell process is mostly used for fabrication of CMOS, and PWell process is also almost similar to the NWell process, but the only difference in PWell process is that it consists of main N substrate, and thus PWells itself act as a substrate for the N device. Here the second process is twin tub fabrication process. Now in this process, a separate optimization of the N type and P type transistor will be provided. Different step of the fabrication of CMOS using twin tub fabrication process as follows. It is exactly similar to the NWell and PWell process, but just the basic difference is that in case of twin tub CMOS fabrication process, both NWell and PWell process is applied on a substrate. That means two wells are formed inside the substrate. That's why it is called twin tub fabrication process. Now the steps involved in CMOS twin tub fabrication process are: first, lightly doped N ions or P ion substrate is taken, and to protect the latch up epitaxial layer is used. The high purity control thickness of the layer of silicon are grown with exact dopant concentration. The dopant and its concentration in silicon are used to determine electrical properties. Then the formation of tub is done. Then the thin oxide construction is done. After that, implementation of source and drain terminals are done. Then cut the making contacts, and last process is the metallization process. Now here, this process can be done like this. By using the above step, by using this type of steps, we can fabricate the well process or twin tub process. In case of twin tub process, both PWell and NWell for NMOS and PMOS transistor are formed on the same substrate. The main advantage of this process is that the threshold voltage, then body effect parameters, and the transconductance can be optimized separately. The starting material for this process is again the P substrate, and a epitaxial layer is grown over the P substrate layer, which is also called as EP layer. Then the process steps for twin tub fabrication process is similar to the process we just studied for the NWell and PWell fabrication process. Just the difference is that both type of NWell PWell fabrication process is implemented on twin tub fabrication process. Now in this case, first a thin layer of silicon dioxide is deposited, which is served as a pad oxide. Then thicker silicon nitride layer is deposited by chemical vapor deposition process. Then plasma etching process is used to create the trenches and for insulating the devices. Then trenching are filled with silicon dioxide, which is called the field oxide layer. Then again the same process is provided. A PWell mask is used to expose only for PWell areas, and NWell mask is used to expose only the NWell areas. And then after the ultraviolet rays passing process and masking process, we etch the both NWell and PWell so as to form the twin tub MOSFETs by using both type of NWell and PWell. Now next step we are going to discuss is the latch up triggering. Now what is this latch up triggering in CMOS, and what is the latch up issue in CMOS design? So in simplest way, if we discuss the latch up triggering, the latch up issue can be defined as the formation of direct path from VDD supply terminal to ground supply terminal in the design, which will cause huge current flow between the two power terminal rails, and this creates the short circuit path between supply VDD and ground terminals, and this is the main issue called as latch up issue in CMOS. Now see, this is the diagram of CMOS fabrication process. Here we study the diagram of a simple inverter in which we fabricate both NMOS and PMOS transistor. Here P substrate is used, in which two N layer is formed to form the NMOS, and NWell is formed in which two P substrate P diffusion is fabricated, which forms the PMOS transistor. Now both NMOS and PMOS transistor can be formed using this NWell as well as PWell process. Now as shown in the figure, a PNP device formed inside the CMOS can be, and this can be triggered by various means. Once the PN device is triggered by any mean, the latch up event will start, and some of the main reason is due to noise at the output terminal, or electrostatic discharge event, or ionizing radiation, etc. Now how this latch up is formed? As shown in the above figure, a PMOS device is formed inside the NWell and a NMOS device is formed on the P substrate region. If we see the region below the source or drain of the PMOS device, a source or drain is formed with P ion implantation. Then NWell comes, and below the NWell there is a P substrate. So a parasitic PNP bipolar junction transistor is formed. Here, whose emitter is the source of the PMOS, the base is the NWell, and collector is P substrate. In similar manner, a parasitic NPN BJT is formed near the NMOS device, whose emitter is the source of the NMOS. As shown in this figure, and base is the P substrate and collector is the NWell. Both these BJTs are interconnected with each other in such a way that they form a PNPN device. The base of PNP BJT, here as shown in this diagram, is connected to the collector of NPN BJT, and base of NPN BJT is connected to the collector of NPN BJT. A PNPN device is formed in off state, and there are terminal current or no current flow through it. But once the PNPN devices get triggered by its gate signal, a large current starts to flow through it, and it continues to flow even if the gate signal is removed. This figure shows the PNPN device and its characteristics. See, here this is the parasitic diagram form of BJT inside the CMOS device, and this creates this triggers both PNP and NPN transistor. That's why a direct supply path between VDD and ground will form when this both BJT gets triggered out, and this creates a short circuit path between VDD and ground, and this is called as latch up triggering. Now question arises, how do we prevent the latch up triggering? What is the process to prevent the latch up triggering? The most effective way to prevent the latch up through substrate and well tap connection. If we use a tap NWell to VDD or tap the P substrate to ground, this is the process by using which we try to prevent the latch up triggering. Then third one is putting a high resistance in the path so as to limit the current through supply and make gain of PNP transistor and gain of NPN transistor. Product of this both gain less than 1. This is the way we try to prevent the latch up. Then fourth number is surrounding the PMOS and NMOS transistor with an insulating oxide layer. This break the parasitic SCR structure. Then next is the latch up protection technology circuit, which shut off the device when latch up is detected. These are the some prevention technique which we can use to prevent the direct latch up triggering inside the CMOS transistor. This is all about the latch up prevention technique.